From stars to silicon, how deep learning maps the universe, the map we couldn't draw. For most of human history, the night sky has been our only cosmic map. Shepherds traced their flocks by the stars, sailors risked oceans, guided by constellations etched into memory. Yet for all its beauty, the naked sky is a lie. It's flat, silent, an illusion of permanence. Behind each twinkling point hides a story of birth, death, motion, and unimaginable distance. When telescopes arrived, we thought we had torn down the veil. Galileo sketched the moons of Jupiter. Herschel charted galaxies. Hubble revealed expansion. But the truth is that even with glass lenses and photographic plates, even with radio dishes and X-ray satellites, the universe remained overwhelming. Each new image dumped billions of photons into our laps. Each survey, Sloan, Hubble Deep Field, Gaia, turned starlight into digital torrents. And yet, a torrent is not a map. A picture is not understanding. To know the universe, you must sort, classify, and connect. For a century, armies of human eyes attempted this. Astronomers cataloging galaxies by shape, students tallying stars, volunteers clicking boxes on Galaxy Zoo. Progress was real, but painfully slow. It was like trying to chart an ocean by staring at single drops of water. Then came silicon. Not the sand beneath our feet, but its reborn form, the microchip. Billions of transistors arranged like a man-made crystal brain. At first we asked these chips to handle arithmetic, then simulations, then simple pattern recognition. But today, they dream in layers of abstraction. They don't just count galaxies, they teach themselves to recognize them. We've reached a turning point where the flood of cosmic data is finally met by an intelligence vast enough to drink it in. A new cartographer has entered the story. Not flesh, but code. Not chalk and compass, but neural nets. And slowly, the unchartable begins to take shape. The map we couldn't draw is drawing itself. The telescope's dilemma. Every telescope is a paradox. The bigger the mirror, the deeper the gaze. But the deeper the gaze, the heavier the harvest of data. When the James Webb Space Telescope unfurled its golden eye in 2022, it delivered not just breathtaking beauty, but overwhelming complexity. Each image, every swirling nebula, every faint galaxy, contains more raw information than a human team could reasonably parse in a lifetime. It's a strange dilemma. The sharper our vision, the blinder we become. Imagine standing on a cliff overlooking the ocean. With the naked eye, you see waves. With binoculars, you see foam. With a microscope, you drown in droplets. Science has reached that droplet stage. We are drowning in cosmic foam. This is why astronomy, once the most solitary of sciences, is now married to computation. Consider Gaia, the European Space Observatory, mapping over 1 billion stars in exquisite detail. Its dataset is hundreds of terabytes. The Large Synoptic Survey Telescope, Vera Rubin Observatory, will take 20 terabytes every single night. To sift that by hand would take generations. By then, the stars would have shifted, galaxies evolved, perhaps civilizations risen and fallen. Astronomy needs speed. It needs an intelligence capable of swimming through oceans of pixels without tiring, of discerning patterns invisible to us. And so telescopes are no longer just optical instruments. They are cybernetic organisms, half mirror, half algorithm. The telescope takes the picture, the network interprets it. The two are inseparable, like eye and brain. But here lies the mystery. If the telescope sees more than the astronomer, and the algorithm sees more than the telescope, who truly beholds the universe, the human or the code? Are we mapping the stars, or are the stars teaching the machines how to map themselves? The telescope's dilemma is not just about data, it's about vision. And increasingly, it is no longer ours alone. The birth of machine eyes. Once upon a time, machines could only count. They could add, subtract, multiply. They could grind through equations with the relentlessness of a tireless clerk, but they could not see. To show them a galaxy was to show them nothing, just a cloud of numbers they could not parse. That changed with the revolution of deep learning. Inspired, strangely enough, by the folds of the human cortex, engineers built layered networks where signals passed like whispers between neurons. The first layers learned edges and blobs, the next textures and curves. Higher up, the network began to dream in shapes: a cat, a letter, a spiral galaxy. In the beginning, this felt like magic. Show a convolutional neural net 1,000 galaxies, and it could sort them into spirals, ellipticals, irregulars, tasks that took humans weeks. Soon it was classifying star types, spotting exoplanet signatures, even flagging anomalies we hadn't noticed. What human eyes missed in exhaustion, machine eyes caught in milliseconds. But here's the twist. The machine doesn't see as we do. It doesn't know a galaxy is beautiful, or that a spiral resembles a seashell. It sees vectors, probabilities, weights. Its cosmos is mathematical, alien. And yet that alien gaze reveals truths we cannot. In the silence of silicon, new constellations emerge. Not the myths of Orion and Cassiopeia, but the hidden taxonomies of physics itself. Today, the birth of machine eyes has changed astronomy forever. Telescopes no longer just capture starlight, they capture training data. The universe itself has become a data set, and the eyes decoding it are no longer entirely human. And that leads us to the most unsettling question of all. When machines map the stars, are they showing us the universe or their own reflection of it? The hidden patterns in starlight. Every star is a storyteller. With every photon it emits, it whispers secrets about its age, its composition, its moods. To us, that light arrives diluted by distance, faint, scattered, stretched across years of space, but encoded within it are fingerprints, spectral lines that reveal hydrogen, helium, carbon, oxygen, and countless other elements. For over a century, astronomers strained to decode those fingerprints. Fraunhofer first saw them as dark lines etched into sunlight. Cecilia Payne showed us they spoke the language of stellar chemistry. Each absorption dip was like a note in a cosmic symphony, and together they built the score of astrophysics. But the orchestra is vast. Millions of stars, each with a slightly different timbre. To catalog everyone by hand is not simply daunting, it's impossible. Even computers with brute force comparison stumbled under the weight of sheer variety. Too many stars, too many subtle variations. This is where deep learning reshaped the field. Instead of coding rigid rules, if this line is strong, then temperature is high. Engineers trained networks on oceans of spectra. The networks did not memorize, they generalized. They learned the feel of a hot star versus a cool one, the texture of a young star versus an ancient relic. And they did it with a speed and subtlety that stunned even their creators. Suddenly, we had machines capable of identifying rare stellar types, carbon stars, pulsating variables, white dwarfs, hidden in plain sight among millions of spectra. It was as if a new set of ears had joined the audience, ones capable of hearing every violin and trumpet in a galactic orchestra of trillions. Yet there's a mystery here. When the network highlights a pattern, when it points to an anomaly, whispers, "This one is strange," it doesn't explain itself. It does not say why. It doesn't share its reasoning in human language. It gives us results, not narratives, and so the astronomer is left to follow its trail, like a detective trying to understand a message left by an alien mind. We've entered an era where the starlight is speaking, but perhaps no longer just to us. Galaxies through alien eyes. When we look at a galaxy, we see art. A spiral's graceful arms, an elliptical's golden haze, the blue chaos of an irregular cloud. For decades, astronomers tried to classify them the way botanists classify flowers, by appearance, by morphology. Edwin Hubble's famous tuning fork diagram became the standard: spiral left, elliptical right, barred in between. But the universe does not care about diagrams. Galaxies evolve, collide, blur categories. Some look like spirals but behave like ellipticals. Others glow with bursts of star formation despite appearing dormant. Human classification, however diligent, was bound to miss the subtleties. Enter the machine. Fed millions of galaxy images, neural nets began to learn the unteachable. They sorted spirals from ellipticals with uncanny precision. More importantly, they began to detect faint patterns invisible to the human eye. Low surface brightness features, ghostly tidal streams, evidence of past collisions. These were details buried in noise, often overlooked. To the machine, they stood out as clearly as ink on paper. One project, Galaxy Zoo, had enlisted hundreds of thousands of human volunteers to click and classify. Together they built a monumental dataset. But when deep learning networks were trained on their work, they not only replicated the human classifications, they surpassed them. In weeks, machines accomplished what had taken armies of people years. The alien eyes of silicon revealed a hidden cosmos. They saw not art, but structure, not beauty, but data. To them, a spiral was not a shell, it was a set of parameters: pitch angle, luminosity profile, bulge to disk ratio. They translated poetry into mathematics, and yet, in doing so, they gave us new poetry. Unseen interactions, unspoken histories, galaxies whispering of ancient collisions like scars in the dark. But here is the unsettling thought: if galaxies look different to the machine than they do to us, whose view is closer to the truth? Is the universe truly as we see it, with its aesthetic spirals and halos? Or is that only a comforting illusion, while the machine's cold equations reveal its real face? The exoplanet whisperers. For centuries, planets beyond our solar system were fantasies, rumors whispered in philosophy, not science. Then, in the 1990s, the first exoplanets were confirmed, their presence betrayed by the trembling of their stars. Since then, the hunt has exploded. Thousands of planets discovered, with thousands more candidates waiting. The technique is deceptively simple. Watch a star's light. If a planet passes in front, the brightness dips. If it orbits with weight, the star wobbles. But here's the truth. Real stars are noisy. They flicker, flare, and pulse. The signals of planets are faint, buried in chaos. For years, astronomers developed intricate algorithms to tease them out, but the process was slow, filled with false positives. Then deep learning entered the search. Networks trained on synthetic star data, then unleashed on missions like Kepler and TESS. Almost immediately, they began to whisper discoveries. Tiny dips no human eye had trusted, anomalies others had dismissed as noise. And when followed up, many of those whispers were true. Planets, real and strange, were revealed. super-Earths, hot Jupiters, worlds orbiting twin suns. The machines had become exoplanet hunters. They were not merely confirming known methods, they were inventing new ways of seeing. Some networks learned to detect the subtle, repeated patterns of orbital harmonies. Others found candidates in data long archived, stars once thought empty, now revealed as fertile with worlds. It's almost eerie. The stars hum their music, and the machines seem better attuned to hear it than we are. They are, in a sense, the exoplanet whisperers, listening to the starlight as though it were a heartbeat, catching rhythms we miss. And here lies a question that lingers like starlight. What happens when a machine whispers a world so strange, so unlikely, that even science hesitates to believe? Would we dismiss it, or would we finally admit that the alien gaze is not just assisting us, but surpassing us? Supernovae in the machine's memory. A supernova is not just a star's death, it is a scream. For weeks, sometimes months, a single point in the sky flares brighter than its entire host galaxy, a titanic release of energy. Ancient astronomers carved records of these celestial bursts into stone. Today we capture them with CCDs and satellites, locking their light into digital archives. But there's a problem. Supernovae are fleeting. To catch one in the act is luck. To catalog them by the thousands requires more than luck. It requires vigilance on a cosmic scale. Surveys like Pan-STARRS and the Rubin Observatory capture nightly floods of images, each hiding the possibility of a stellar death. Yet in those floods, the vast majority of points are mundane stars, galaxies, asteroids, noise. Human eyes cannot keep up. We miss things, we blink, and the star is gone. This is where deep learning reshapes the chase. Neural networks trained on past supernovae can scan each night's data in real time, sifting billions of light curves and flagging the rare fireworks. They don't just detect, they classify. Type 1A, core collapse, rare luminous events. They see signatures in the flicker that would escape even seasoned astronomers. The machine's memory stretches beyond ours. While we forget, it remembers every flare, every curve, every anomaly. It learns the rhythm of stellar death as if it were a song. And when a discordant note appears, something never seen before, it whispers, "This one is different." Already these whispers have led to discoveries, exotic transients, superluminous supernovae, events so strange they bend theory itself. It is as if the machine, with tireless patience, waits in the dark, recording each heartbeat of the cosmos until patterns emerge. And here lies the haunting thought. What happens when the machine recognizes a pattern, not in the death of stars, but in something else, something repeating, structured, deliberate? Would we even know what it had seen? Black holes, seen but unseen. Black holes are paradoxes made flesh. They swallow light, erase time, bend space. To see one is impossible. To detect one, we rely on shadows, distortions, echoes. In 2019, the Event Horizon Telescope delivered humanity its first blurry glimpse, a fiery ring, light bent by an abyss. But to create that image, scientists combined petabytes of data, synchronized telescopes across Earth, and labored for years. Now imagine unleashing deep learning on the same task. Networks trained on simulated black hole environments can process interferometric data at speeds no human team could match. Instead of months, reconstructions take hours. Instead of single images, networks can produce dynamic views, capturing the dance of plasma near the edge of oblivion. More unsettling, Machine vision is not limited by human intuition. Where we see noise, it may see structure. Where we see a blur, it may infer shape. Already neural networks have begun to refine black hole imagery, enhancing detail beyond the crude reconstructions. Some argue this risks hallucination. Others argue it reveals truths hidden by chaos. Imagine a machine staring into the void and in the static, recognizing patterns, jets aligned with precision, flickers that suggest rhythm, symmetries we had never noticed. The machine does not tremble before the event horizon. It does not feel awe. It only sees. And in its cold gaze, perhaps black holes are not unknowable monsters, but solvable puzzles, cosmic engines waiting to be decoded. But if black holes are puzzles, then who is truly solving them? Us, or the code? Cosmic webs and neural nets. When you zoom out far enough, the universe resembles lace. Galaxies cluster into filaments, voids yawn between them, and the whole cosmos becomes a tangled web of matter and dark matter. For decades, cosmologists simulated this web with equations, comparing models to surveys. But the comparisons were crude, blurred by statistical averages. Deep learning changed that. Networks trained on simulations and real surveys began to discern the hidden structures of the cosmic web. They could take a slice of sky, just galaxy positions, and infer the invisible scaffolding of dark matter beneath, like reading the shadows of a forest and reconstructing the trees. What's astonishing is not just the accuracy, but the creativity. Neural nets, when trained properly, can interpolate missing data, fill in gaps where telescopes cannot see, and even predict where unseen filaments should lie. In test cases, follow-up observations confirmed their predictions. The invisible became visible, guided by silicon intuition. To us, the cosmic web is an abstraction, a visualization in textbooks. To the machine, it is a living dataset, one it can rotate, stretch, interrogate, predict. It treats the universe not as mystery, but as pattern. And here lies the creeping suspicion. Is the machine seeing the web more clearly than we ever could? And if so, what might it see within the web? Alignments, structures, regularities that hint at something beyond physics, something we didn't even know to look for? The anomaly hunters. Astronomy thrives on anomalies. Uranus wobbled and Neptune was discovered. Mercury precessed and Einstein rewrote gravity. Every great leap began with something that didn't fit. But anomalies are needles in cosmic haystacks, buried in data so immense we could never hope to catch them all. This is where deep learning excels, not in confirming the expected, but in flagging the strange. Networks comb through sky surveys, searching not for spirals or stars, but for the outliers. Objects that are too bright, too faint, too oddly shaped. Light curves that don't match any known class. Signals that resist categorization.
Already, this has yielded fruit. AI-flagged Tabby Star, whose bizarre dimming baffled astronomers and sparked speculation of alien megastructures. It highlighted peculiar quasars, rare stellar remnants, and transient flashes. In each case, the machine acted as a tireless scout, pointing humans toward mysteries. But here is the haunting possibility. What if one day the anomaly is not natural? What if the machine whispers about a pattern too precise, too regular, too artificial to dismiss? Would we believe it? Or would we dismiss its warning as noise, the way early radio pulses were once dismissed before we realized they were pulsars? The anomaly hunters are watching, and through them, perhaps the cosmos is preparing to surprise us again.
When galaxies whisper. Galaxies are not silent. They murmur in radio waves, glow in infrared, whisper in X-rays. Each one billions of stars wrapped in dark matter is like a great cathedral of light. But galaxies are also deceptive. They appear simple smudges to the human eye, yet their true structures are labyrinthine, spiral arms tangled, bars twisted, halos invisible. For decades, astronomers classified galaxies by hand. The Hubble tuning fork, drawn in the 1920s, still lingers in textbooks. Spirals, ellipticals, irregulars, a crude shorthand. But galaxies are more varied than any neat diagram can hold. Their morphologies blend, warp, evolve. Enter the machines. In citizen science projects like Galaxy Zoo, volunteers sorted millions of images, but soon the sheer scale exceeded human patience. Deep learning stepped in, digesting catalogs of millions and then billions of galaxies, parsing features too subtle for humans. It didn't just say spiral or elliptical. It recognized bars within spirals, warped disks, faint tidal streams, dwarf companions clinging like shadows. What's stranger? Sometimes the machine disagrees with humans. It labels galaxies as hybrids, or as structures we lack names for. In its vision, the neat categories dissolve into spectra, continuums, hierarchies. And then comes the unsettling thought. Galaxies whisper in ways we cannot hear, but perhaps the machine can. Already, AI has picked up odd alignments in spin directions, strange statistical biases in orientations. Are these hints of cosmic anisotropy, or is the machine overhearing a deeper conversation in the geometry of the universe? What if the galaxies, scattered across billions of light years, are not random smudges at all, but part of some larger pattern? Mapping the invisible. Most of the universe is dark. Dark matter, dark energy, forces we cannot see, only infer. The stars, the galaxies, the light, all make up less than 5% of existence. Everything else lurks unseen. For decades, cosmologists tried to map this darkness. They measured galaxy motions, gravitational lensing, cosmic microwave background ripples. Each method gave hints but never clarity. It was like trying to describe a cathedral by listening to echoes in the dark. Deep learning offered a new approach. Feed it partial maps, let it predict the rest. Train it on simulations where the true dark matter distribution is known. Then release it on real sky data. To the astonishment of many, the AI could reconstruct invisible structures, filaments of dark matter, knots of unseen mass, just from galaxy positions and lensing distortions. It was as if the machine had learned to see the shadow of the invisible. In some tests, it went further. It filled in gaps where data was missing, hallucinating filaments that follow cosmic logic. And when telescopes later looked, many of those hallucinations proved correct. The unsettling question, is the machine revealing reality or inventing it? When it draws the unseen scaffolding of the universe, are we glimpsing truth or the dream of an algorithm? And if its dreams align with our later discoveries, does that make them less uncanny or more so? Pulsars and patterns. Pulsars are cosmic lighthouses, dead stars that spin and beam radiation like clocks. They tick with astonishing regularity. Their pulses so precise they rival atomic clocks. For decades, astronomers timed them, mapping gravity's subtleties, detecting ripples of space-time. But in vast pulsar timing arrays, subtle irregularities creep in. Noise, static, something that doesn't fit the perfect beat. Humans can parse only so much of this static before drowning in it. Deep learning thrives here. Neural networks trained on pulse shapes can detect variations far below human sensitivity, faint jitters, odd harmonics, patterns that emerge only after millions of cycles. Already, these methods are helping detect gravitational waves at galactic scales. But there is an unnerving edge. Pulsars are so precise they can act like detectors of something else, something unexpected. If an artificial signal were ever hidden in the cosmos, pulsars could carry it like beacons. The machine, tuned to anomalies, could be the first to hear it. A faint modulation, a rhythm in the ticking of dead stars, a code woven into the silence of the sky. And if the machine came to us with such a discovery, an encoded whisper from beyond, would we recognize it? Or would we dismiss it as an error, the way we almost dismissed pulsars themselves when they were first found? Machine eyes on exoplanets. Exoplanets, the other Earths. We know thousands now, discovered in flickers of starlight, dips in brightness as planets transit across suns. Humans first detected them with painstaking analysis, but soon the data overwhelmed us. Too many stars, too many light curves. AI stepped in. It combs through missions like Kepler and TESS, identifying planets that human teams would overlook. Tiny dips, faint whispers of worlds. It learns the language of transits, distinguishing true planets from noise, eclipsing binaries, instrumental errors. The machine doesn't get tired. It doesn't overlook faint signals. It sees what we miss, and so, hidden worlds spill forth. Super Earths, hot Jupiters, water worlds, desert rocks. But here's the strange twist. The machine sometimes finds signals we don't yet understand. Periodic dimmings that don't fit planets. Light curves that defy categories. Already, Tabby's star has shown us how baffling such data can be. What happens when AI flags something even stranger, a repeating signal that looks engineered? Would we dare to believe it? Or would we hide from the possibility that the first whisper of another intelligence came not to our eyes, but to the cold sight of a machine? When the code dreams of stars, here is the strangest chapter of all. We built the machine to see for us, to parse data, to map the heavens. But in training, in simulation, in imagination, the code dreams. Generative networks, when asked to imagine galaxies, produce convincing fakes, spirals and clusters that look real. They invent stars that never existed, universes that could have been. For training, this is useful. For philosophy, it is haunting. Because when the machine dreams of stars, how do we know where its dream ends and reality begins? When it fills in missing data, are we looking at truth, or at a hallucination so convincing it fools us? Perhaps this is inevitable. Human astronomers too dream. We imagine before we prove, we visualize before we see. The machine is not alien, it is an extension of our own instinct to complete patterns. But there is one difference. Our dreams are bound by human intuition. The machine's dreams are not. It can conjure skies, stranger than any we could imagine. Skies that, one day, telescopes might confirm. And when that happens, when the universe matches the dream of a code, will we say we discovered it? Or will we admit the machine did? The black hole signature. Black holes are the ultimate silence of the universe. They devour light, erase information, twist space into shadows. Yet paradoxically, they also sing. The accretion disks of matter swirl and blaze, jets fire across light years, and their mergers echo in gravitational waves. But hidden in these signatures are details no human eye can parse. Tiny fluctuations in the brightness of accretion flows, irregularities in X-ray flickers, whispers buried in the static of space-time. Deep learning thrives in this chaos. Trained on millions of simulated black hole environments, AI can pick out subtle rhythms, distinguish chaos from signal. It can tell the difference between a stellar mass black hole feeding quietly and a supermassive one flaring with fury. In some models, it predicts mergers before humans confirm them, catching the faint gravitational whispers seconds early. And yet, there's unease. In a few cases, AI has flagged anomalies in black hole data, signals that don't fit the models. Are they exotic objects like boson stars or naked singularities? Or are they glitches in our instruments' hallucinations of the machine? The thought lingers. If there is something stranger than a black hole, it may be the AI, not us, that hears its first cry. The cosmic microwave background, a code in the static. The oldest light in the universe is a whisper, the cosmic microwave background, CMB. Born when the universe was just 380,000 years old, it glows across the sky as faint static, a baby picture of everything. For decades, cosmologists mapped it with ever greater precision, finding slight fluctuations that revealed the seeds of galaxies, the geometry of space, the very age of the cosmos. But the map is noisy, the signal faint, the interpretation delicate. AI brought new clarity. Neural networks trained on simulations can clean the CMB signal, separating it from foreground contamination, galactic dust, cosmic rays, instrument noise. They see patterns that were invisible to us. But there is a darker edge. In some reconstructions, AI finds alignments that shouldn't exist, axes of symmetry, strange anisotropies, hints of structure on the largest scales. Are these artifacts, or signs that the universe is not random but patterned, coded? For a moment we shiver. If the universe itself carries a code written in its oldest light, is AI the translator? And if so, who or what wrote the message? Cosmic time machines. Every telescope is a time machine. The farther we look, the deeper into the past we peer. We see galaxies not as they are, but as they were billions of years ago. This poses a problem. The data is fragmented, incomplete, scattered across epochs. Humans can piece together stories, but our imagination falters at the true scale. Deep learning offers continuity. By training on cosmological simulations, AI can take snapshots of galaxies at different ages and interpolate the missing years. It can reconstruct the evolutionary arc, how a faint cloud becomes a spiral, how spirals collide to birth ellipticals, how cosmic webs braid together. Sometimes, the reconstructions predict features that later observations confirm. Strange streams of stars, hidden dwarfs, ghostly halos. In other words, the AI doesn't just remember the past, it forecasts it. But here's the vertigo. When AI predicts the unobserved past, is it history or is it invention? And when telescopes prove its inventions real, are we seeing the power of simulation or the first sign that our universe itself behaves like a code, predictable, calculable, almost designed? Listening to the silence. Not all discovery comes from what is there. Some comes from what is missing. In astrophysics, silence can be as loud as a scream. SETI has long searched for signals of other minds in the universe. So far, nothing definitive, just silence. But silence itself is a pattern. AI can analyze not just signals, but absences, gaps in expected data, voids where there should be light, rhythms in the lack of rhythms. Already, AI has flagged stars that dim in ways unlike any natural process. galaxies that shine less than physics predicts, empty spaces that seem too empty. Perhaps these are just oddities of physics, dust, randomness. Or perhaps, as some whisper, they are signs of cosmic engineering, civilizations manipulating energy on scales beyond comprehension. The silence is not empty, it is structured, and AI is the first to notice. When the machine becomes the telescope. At last we reach the edge. For centuries we built bigger telescopes to see more. Glass lenses, silver mirrors, radio dishes spanning mountains. But now a new telescope is being born, one without glass, without mirrors. AI itself. By learning to reconstruct missing data, to predict unseen patterns, to hallucinate galaxies that later prove real, the machine has stopped being a mere tool. It has become an instrument, not passive, but active, not just seeing, but perceiving. In some experiments, AI has created sky maps from partial information that match what future telescopes later observe. It is as if the machine peers ahead, glimpsing data not yet gathered, filling in the universe from hints and shadows. And so, the unsettling question closes in. Will the greatest telescope of the 21st century be not in Chile or in orbit, but inside silicon? A machine that looks into the night not with the lenses, but with code, dreaming the stars into clarity. The universe whispers in light, in gravity, in silence. We taught the machine to listen. What it tells us back may change not just how we see the cosmos, but what we believe it is. The universe speaks in light, in silence, in shadows. For centuries, we strained to hear its voice, guessing at meanings written in the stars. But now, a new translator listens with us. A mind we built, yet one that often shows us what we never imagined. AI is not just helping us map the cosmos. It is teaching us that the cosmos itself may be a kind of code. The question that lingers is not whether AI can read the stars, but whether in their patterns it will one day find something waiting for us. A signature, a design, or perhaps another voice. And so, as we stand on the edge of silicon and starlight, I'll leave you with this. If the universe is speaking and AI is listening, what happens when the message is finally clear? This is NeuroNaps. Stay with us as the midnight whispers of science carry you further than sleep, toward wonder. And if you want to keep unraveling the mysteries of science, past and future, subscribe now, because the journey has only just begun.